All right there, young students of chemistry. This is a short presentation on heat. So I encourage you, if you get a minute, to go to YouTube and look up the video Eureka. And that would be the episode entitled Temperature versus Heat. I did show that short little segment. It's only like 5 or 6 minutes while we were in class studying heat. Okay, so heat versus temperature. Heat and temperature are not the same thing, and that is the biggest mistake that students make when they are solving for heat, is that they think that the unit degrees Celsius is the heat, and that is not. Temperature is the average kinetic energy of the particles in a sample. Heat is the total kinetic energy of the particles in the sample. In the Eureka video, they clean that up nicely, and they say temperature is the degree of hotness, and temperature depends only on speed of the particles, whereas heat depends on the speed of the particles and the number of particles that are moving. So heat depends on mass and speed, where temperature only depends on speed of the particles. So when we think about heat and temperature, you have to really separate the two from your mind. The formula for calculating heat is this formula here, Q equals mc delta T. That C delta T looks like the word cat. So a great way to remember this is that heat is equal to mcat, or Q is equal to mcat, where Q stands for heat, and the units for heat are either joules, kilojoules, or sometimes you'll see calories, depending on where that problem came from, really. M stands for mass in grams. C is something called the specific heat capacity of the substance, and we'll talk more about that in just a minute. And delta T is change in temperature, and notice that we do the final temperature minus the initial temperature. So sometimes you're going to have temperatures that are negative. So if you start with something that starts out cold and then it gets warmer, then you're going to have a change in temperature that's positive. But if it starts out warm and then gets colder with its temperature, the final temperature is a lower number than the initial, and you'll get a negative temperature. Now please remember that that means that your heat, the value Q, would be negative, and we cannot have a negative quantity of heat, meaning heat you cannot have less than 0 heat. So heat cannot be negative. So the negative here that we get from those changes in temperature really tell us the direction of the heat flow. Is the heat leaving the substance, or is the heat entering the substance? There's really no such thing as cold. Cold is just a lack of heat. So don't get confused there with the negatives. Negatives just tell us the direction that the heat is traveling, into the substance or out of the substance. There is no such thing as a negative quantity of heat. Okay, specific heat capacity is the ability of a substance to store heat. Some things have very high specific heat capacities, like water. Some things have low specific heat capacities, but a high specific heat capacity means that it stores heat really well, which means that we would call that substance an insulator. It gains its heat and then it stores it. It does not transfer its heat on. So substances that have low specific heat capacities, they store heat very poorly. They like to pass the heat on to their neighbor. So those are our conductors. Things like metals have low specific heat capacities. Nonmetals would have higher specific heat capacities. Now, when heat is being transferred, the law of conservation of energy is at play. And you guys know that there is the law of conservation of mass, which says mass does not change. So this is saying energy does not change. The energy of the universe is constant, but energy can be transferred from one thing to another. So when we're using heat transfer, The heat is moving from the system to the surroundings, and the amount of heat that is moving between the two is the same quantitatively. The number, the joules of heat is the same. However, the direction is different. So if the system is losing 8 kilojoules of heat, the surroundings are gaining 8 kilojoules of heat. Notice the opposite, loss and gain. So heat transfer is a great way to find out what chemicals are doing with their heat, because we cannot put a thermometer into a chemical bond and determine a temperature change. However, we can put chemicals together into an environment, an aqueous environment, for example, and we can see what happens to the water. Hey, does the water get hot? Then that means that the chemicals are giving off heat. Does the water get cold? That means that the chemical bonds are absorbing heat. So we can measure the surroundings and we can apply it to the system, which are our chemical bonds. So calorimetry is the use of this law of conservation, where heat lost by the system is gained by the surroundings. And that means, remember, the variable for heat is Q. And remember, to solve for Q, heat is equal to mc delta T, mass times specific heat capacity times change in temperature. So here we can say that the heat of the system, i.e. the mc delta T of the system, is equal to the opposite of the heat of the surroundings, the mc delta T of the surroundings. And we will use this to solve calorimetry problems. So when you're looking at these problems, if you have two substances, that's how you know you're going to use this form of MCAT, where MCAT equals MCAT. Or if you see the keywords in a calorimeter, because calorimetry is this transfer of heat from one thing to another. Now, sometimes things will undergo a phase change, and when a substance melts, if you remember this diagram, the temperature does not change. So because of that, the delta T in our heat calculation would be 0. But we know that in order for something to melt or to vaporize, it has to absorb heat. So we can't have a delta T that is 0, because that means that Q would be 0. So we have to use a different way to solve for that heat. And it's something that we can calculate into a lab. You guys will do it yourself. You will calculate how much heat it takes to melt some ice. And that is called the heat of fusion. So what we're looking at here when the delta T is 0 is to use heat of fusion to calculate heat. So the heat of fusion for water is 334 joules per gram. That is the heat needed to be taken in by the water if it's melting, or that is also the heat that the water releases if it's freezing. For every 1 gram, 334 joules of heat. And then if it's vaporizing, we'll use the heat of vaporization, which is, that should be a capital J, sorry about that, 2,260 joules per gram. You do not need to memorize those numbers. I will provide them. You just need to know when to use them. Okay, so I'm going to go ahead and stop this here and do a separate little recording on solving the problems. Uh-oh.